In this video, we're going to take the time to review the homeworks that we've been doing for the past 3 days. So what we've learned over the course of this week is how to do curve fitting, how to do reduced row echelon form, and also how to work with inverse of matrices, both proving that two matrices are inverses and also learning how to find the inverse for a single matrix. So this is the solutions to homework problem number 130. Starts on page 603. We got to do the problem 69, 70, 71. Problem 69 says they wanted you to curve fit a parabola. So here's the general equation for a parabola. Y equals ax squared plus bx plus c. And the 3 points they gave you had coordinates of 1, 8, 2, 13, and 3, 20. So the key here with curve fitting is that you're actually going to be building your own equations. Remember, the first coordinate is your x, and the second coordinate is your y value that you're going to plug into the equation. So I'll be putting the 1 into here as x and squaring it and multiplying it with a, so that's 1a. I'll be putting the 1 in here as the value of x and multiplying it with b, so that's 1b and c. And then the 8 goes in as the y coordinate. So the first equation that I'm generating is a plus b plus c equals 8. That comes from using the coordinates of the first point. Plugging the coordinates of the second point in, 2 being the value of x and squaring it, gives me 4 times a, 2 times b plus c makes my y coordinate of 13. So there's my second formula, 4a plus 2b plus c equals 13. And the third equation is going to come from using 3 as my x coordinate, squaring that's 9, multiplying it with a gives you 9a, 3 times b plus c equals your y coordinate, which is 20. So my third and final equation is 9a plus 3b plus c equals 20. At this point, you now have your system of equations that you need to solve. So we're going to be putting these values into an augmented matrix. My top row is going to be 1, 1, 1, 8. My second row is going to be 4, 2, 1, 13. And my bottom row is going to be 9, 3, 1, 20. Those are just coming from the coefficients and constants of your equations. So we're now going to do Gaussian elimination. We want to get the top row, left-hand corner, to be a 1. It is. We're going to use the top row multiplied by -4 and add it with the middle row to change this into 0, -2, -3, -19. You're then going to want to take this middle row and divide everything by -2 so that you could turn this spot into a 1. So that'll give you 0, 1, 1.5, 9.5. Then the next thing you have to do is get rid of this 9 right here. You're going to use the top row multiplied by -9 to add with the bottom row to help eliminate that 9. That's going to give you a new bottom row of 0, -6, -8, -52. Then you're going to use the middle row multiplied by 6 and add it with the bottom row to help get rid of this -6 right here. And that's going to give you 0, 0, 1, 5. At this point, you are in row echelon form. You got your diagonal of 1s and your triangle of 0s underneath it. You're now ready to put the letters back into this. So the bottom row is actually telling you the answer for C is 5. Putting the letters back into the row above it and plugging in 5 as your C value is going to give you an answer for B of 2. And then putting your letters back into the top row and putting your values for B and C into it is going to find that the answer for A is 1. Remember, though, the goal of this problem was to find the equation for the parabola. So make sure you then take the values of A and B and C and plug them back into the formula in their appropriate places. The final answer you should have for this problem should be the equation of a parabola, and it should be an equation, so it should be y equals, or f of x equals, 1x squared plus 2x plus 1. Problem number 70 is pretty much the exact same idea. They're going to give you the coordinates of these 3 points. You plug these coordinates, remember that's an x, that's a y, into the generic formula for the equation of a parabola, and you should generate these 3 equations. 1a plus 1b plus 1c equals 9, 4a plus 2b plus c equals 8, 9a plus 3b plus c equals 5. Take that system of equations, put it into an augmented matrix. You want to get the top left corner to be a 1. It is. Then you want to get rid of the 4 that's in the second row in the first spot. And you're going to do that by multiplying the top row by -4 and adding it with the middle. That's going to give you 0, -2, -3, -28. You then want to turn the -2 right here into a 1. So you'll be dividing this entire row by -2. That's going to give you 0, 1, 0, 1, 1.5, 14 in the middle row. The next thing to do is to get rid of this 9. So you're going to use the top row multiplied by -9 and add it with the bottom row. That's going to give you a new bottom row of 0, -6, -8, -76. And then you're going to use them. The next thing to do is get rid of this -6 right here. So you're going to use the middle row multiplied by 6 to add with the bottom row. That's going to give you a new bottom row of 0, 0, 1, 8. You now have your diagonal of 1s and your triangle of 0s underneath it. So we're ready to put our letters back into this and find our answers. The bottom row is telling you the answer for C is 8. The middle row, when you plug the values back in, tells you the value for B is 2. And putting the letters back into the top row and plugging in the values for B and C is going to help you find that A is -1. Again, make sure that you make an equation out of your final answer. It should be y equals -x² plus 2x plus 8. So the last problem that they ask you to do in this homework is problem number 71, where they're going to ask you to curve fit a cubic. So the equation for a cubic is y equals ax cubed plus bx squared plus cx plus d. Notice this is bigger, obviously, than a parabola, and that is the reason for them giving you 4 points for this problem. We need 4 points for this problem because there are 4 coefficients, a, b, c, and d, that we're going to have to find the values of. Remember, x's and y's are given to you in these coordinates of the points. So the coefficients are actually variables for this problem. So again, we're going to start off by taking our x and our y coordinates and plugging them into our generic equation to make an equation for this particular cubic. So the first set of points should give you the equation -8a plus 4b minus 2c plus d equals 2. And the coordinates right here should give you -1a plus b minus c plus d equals -1/4. These coordinates, when plugged into this equation, should give you a plus b plus c plus d equals -7/4. And this last set of coordinates right here should give you the equation 8a plus 4b plus 2c plus d equals 2. And again, you're going to start off by making an augmented matrix. I actually did something first in this particular problem before I even put it into the augmented matrix. I noticed that the best equation to be my top row should be this guy. And the reason why this equation would make the best one for the top row is because it has a coefficient of 1 in front of where the a is. That is exactly what you need in the top row right here. So I'm going to promote this equation up to the top row, and I'm going to move the equation that was in the top row all the way down to the third row. So that's how I made my augmented matrix. One of the things you're going to notice right away about this augmented matrix is it's bigger than what we've been dealing with. So instead of a 3x3, this one is working with a 4x4 matrix of coefficients. Same process, but going to be longer because it's going to take us a while to get to what we want. So I'm going to take the top row and add it with the second row to help me get rid of this -1 right here. That's going to give you a new second row of 0, 2, 0, 2, -2. You then want to turn this spot into a 1, so you're going to divide everything in that row by a 2. That's going to give you 0, 1, 0, 1, -1. The next thing to do is to turn this spot into a 0. So I'm going to use my top row multiplied by top row multiplied by an 8 to add together with this third row. And that's going to give you a new third row of 0, 12, 6, 9, and then -12 on the other side. The next thing that you're going to want to do is get rid of this 12 right here. And the way that you're going to do that is by multiplying the second row by -12 and adding it with the bottom row. And that will give you a new third row of 0, 0, 6, -3, 0. You then want to turn where the 6 is into a 1. So you'll be taking this entire row right here and dividing everything by 6. That'll give you a new third row of 0, 0, 1, -1/2, 0. You then want to get rid of this 8 that's in the bottom row in the first spot. And we always use our top row to help put things in the first column. So you multiply the top row by -8 and add it with the bottom. That's going to give you 0, -4, -6, -7, 16. Then you want to get rid of this -4 that's in the bottom row. We're going to have to multiply the second row by a 4 and add it with the bottom, which is going to give you 0, 0, -6, -3, 12. The next thing you're going to want to do is get rid of this -6 in the bottom row by multiplying the third row by 6 and adding with the bottom. That's going to give you 0, 0, 0, -6, 12 in the bottom row. And the last thing to do is turn this -6 into a 1. You'll do that by dividing everything in the bottom row by -6. And that's going to give you 0, 0, 0, 1, -2. That took a lot more work than normal because this had 4 equations with 4 unknowns. But notice you have the diagonal of 1s and the triangle of 0s underneath. We're now ready to put the letters back in. So this bottom row is telling me the answer for D is -2. Putting the letters back into the row above it is going to help you figure out the answer for C is -1. Putting the letters back into the row above it is going to help you figure out the answer for B is 1. And putting the letters back into the row above it and substituting all those numbers in is going to help you figure out the answer for A is 1/4. Don't forget to take all those values for A, B, C, and D and put them back in to make an equation for a cubic. So y equals, forget to make it an equation, y equals 1/4 x cubed plus x squared minus x minus 2. So homework number 131 starts on page 625. You had to do problems 1 and 3. You didn't have to do 5. So they gave you 2 matrices, a matrix A and B, and they asked you if they were inverses of each other. When given 2 matrices, the way you check to see if they're inverses of each other is you multiply them together. So I took matrix A, which had 2, 1, 5, 3, and matrix B, which had 3, -1, -5, 2, and I put them in that order and I multiplied them together. That produced this result right here, which is an identity matrix. And remember, when you do A times B, you are not done. You would then have to reverse the order of this, putting matrix B first, matrix A second, and then multiplying them together again and proving that the answer still turns out to be an identity. If it turns out to be an identity both ways, which it did, that means that A and B were inverses of each other. If any one of these numbers wasn't a 1 or a 0, or if they were 1s and 0s but they're in the wrong spots, they would not be inverses, but both of these did turn out to be identities, so they are inverses. The exact same thing is going to happen in problem number 3. They give you 2 matrices, you're expected to multiply them together, the answer turns out to be an identity. Remember, you're not done. When it works out to be an identity the first way, you have to reverse the order, putting matrix B first and then matrix A second, and redo the multiplication. This kind of multiplication was not commutative, so we have to show it both ways. And yes, this actually does turn out to be inverses as well. The more challenging problems with inverses are not when they give you 2 matrices and ask you to prove they're inverses. The more challenging problem is when they give you only 1 matrix and they ask you to figure out what the inverse might be. So you're going to take the matrix they give you. In this case, in problem number 9, it was 2, 0, 0, 3. You're going to check to make sure it's a square matrix. It's got to have the same number of rows as columns, which it does. If it does, then you're going to attach an identity matrix of equal size. So this has 2 rows, 2 columns. I need an identity matrix with 2 rows and 2 columns, separated by a dotted line. We then want to use the Gauss-Jordan process to turn this matrix on the left into an identity matrix. And whatever math you're doing, you got to carry it all the way across the dotted line, because this side of it will turn into the inverse. So the first thing I want to do here is turn my top row into a 1 right here where the 2 is. So I'll have to divide everything in the top row by a 2. That's going to be 1, 0, 1 half 0. And in the bottom row, I will want to turn this into a 1, which means I'm going to have to divide everything in the bottom row by 3. 0, 1, 0, 1/3. When this side looks like an identity matrix, this side contains your inverse matrix. So make sure that you identify that this is the answer. 1 half, 0, 0, 1/3. You might even want to write that out separate, like I did here. Problem number 11 is this process. This is the matrix they gave you, 1, -2, 2, -3. It was square, so I attached an identity matrix of equal size next to it. I wanted to make sure that the top left corner was a 1, and it is. So then I used the top row multiplied by -2 to turn this spot into a 0. So that's going to give me a new bottom row of 0, 1, -2, 1. The next thing I would have to do is normally turn this spot into a 1, but it already is. So I'm now in what we would call row echelon form. And we are not done with this process yet, because that's when we have to start the Jordan part of the process. We are now going to use this bottom row and add it to the row above it to help eliminate things that are above the diagonal. In this case, we got to get rid of that -2. You'll have to multiply the bottom row by 2 in order to add it together and eliminate. So the new top row is going to turn into 1, 0, -3, 2. And remember, when this side looks like an identity, this side is containing your inverse matrix. So the answer to this problem is -3, 2, -2, 1. You may even want to label that as its own inverse. Here's the solution for problem 13. Again, this was the matrix they gave you. Matrix A was -1, 1, -2, 1, and it is square. So I'm going to attach an identity matrix of equal size next to it. I'm going to start to go through the Gauss-Jordan elimination process. So the first thing that needs to happen is this spot needs to turn into a 1. So I negated everything in the top row. That gives me a new top row of 1, -1, -1, 0. The next thing that I did, and I actually tried to combine it into one step, but the next thing I did is I needed to turn this -2 spot into a 1. So I multiplied this top row times 2 and added it with this bottom row. That's going to give you a new bottom row of 0, -1, -2, 1. I then need to turn this spot right here into a +1. It's currently a -1, so it's just the wrong sign. So I'm going to change all the signs in the bottom row by negating everything. That's going to give me 0, 1, 2, -1. And at this point, you're in row echelon form, and you'd have to now do the Jordan part, which wants you to get rid of that -1 above the diagonal. So you're going to add the bottom row to the top. When the left-hand side looks like an identity matrix, the right-hand side now contains your inverse. So the inverse matrix for this problem is 1, -1, 2, -1. In both of the two remaining questions for this homework, something funky happens. This is problem number 15, and it starts out looking normal enough. We have a square matrix, 2, 4, 4, 8, has the same number of rows and columns, so I'm going to put an identity matrix next to it. And the first thing I did here is I wanted to turn my top left corner into a 1, so I divided everything in the top row by a 2. That's going to be 1, 2, 1/2, 0. And now I'm going to use the top row to help me get rid of this 4 right here. So that means I'm multiplying my top row by -4 and adding with the bottom. The whole reason that I'm doing this is I'm trying to eliminate the 4 and turn that into a 0. But something weird happens. When I multiply the top row by a -4 and add with the bottom, not only do I get a 0 right here, but I also get a 0 right here. -4 times 2 added together with 8 makes 0. If an entire row on the left-hand side turns into all zeros, there's no way to fix that. Once that happens, there's nothing you can do, there's nothing you can multiply or divide by that's going to change this. So what that means is this matrix did not have an inverse. That is what we call a singularity. Now, the other question where something weird happens is number 17. Because the matrix they gave me, hopefully you were checking it out, was not square. I believe it had more rows than columns. So if your number of rows and columns do not match, you do not have an inverse. You don't even have to do any work for this. You just immediately say no inverse, and that problem is done. So with homework number 132, we're not really learning anything new, but we're learning how to expand what we've already learned out to having 3 rows and 3 columns. So the first 3 problems, problems 2, 4, and 6, were ones where they gave you 2 matrices and asked you to prove whether or not they're inverses. Remember the plan for that, whether you have 2 by 2s or even 3 by 3s, your goal is you want to multiply the 2 matrices together and show that it turns out to be an identity. Now, if it works the first way, if it works when you do A times B, then you have to reverse the order and try again the opposite way and make sure that also turns out to be an identity. If both ways turns out to be an identity, then they are inverses. Now that actually happens for problem number 2 and problem 4. And in problem 6, even though the matrices are bigger, you still do get an identity matrix with a diagonal of 1s, triangle of 0 below, and a triangle of 0s above. So this is an identity matrix, just bigger. And then when it works the one way, you got to remember to go back, reverse the direction, do B first, A second, and multiply it again, and make sure you get an identity matrix, which you do. In problem 16, the matrix that you start with is 2, 3, 1, 4. It is square, and they ask you to find the inverse for this matrix. So I attached an identity matrix of equal size, and you go through the Gauss-Jordan process by first. Actually, the very first thing I did here was I took this entire top row, and I took my entire bottom row, and I switched the order. I moved the top row down to the bottom and the bottom row up to the top. Remember, that is one of the things you're allowed to do in the Gaussian elimination process. Just make sure if you're moving a row from bottom to top or top to bottom, that you take what's on the right-hand side of the dotted line with it. So this 1, 4, 0, 1, the whole thing moved up to the top. And the 2, 3, 1, 0 came from the top and moved down to the bottom. Okay, so I now have a 1 in my top left corner. The next thing to do is to turn this 2 into a 0. So you're going to have to multiply the top row by -2 and add with the bottom. It's going to give you 0, -5, 1, -2. The next thing to do is turn this -5 into a 1, so you're going to have to divide everything in this row by -5. That's going to be 0, 1, -1/5, 2/5. And last thing to do is to turn the 4 into a 0. So you're going to multiply the bottom row by -4 and add it with the top. So remember, what's on the right-hand side here, this is your inverse matrix. So this is your answer over here. Not over here, not the whole thing, just what's over here on the right-hand side. Number 18 in this homework did not have an answer because the matrix they gave you was not square, so it's not going to have an inverse. The problem in this homework that was going to be the longest one was problem number 20. So 1, 2, 3, 4, 5, 6, 7. This was going to take 7 steps. There's no shortcutting this. This is why inverses are so hard. The matrix they gave you, matrix A, was 1, 2, 2, 3, 7, 9, -1, -4, -7. It is square. It has the same number of rows and columns. So I attached an identity matrix of equal size, and then you just start going through the Gauss-Jordan process. So the first thing to do is get rid of that 3. That gives you this new middle row. Then the next thing to do would be to turn this into a 1, but it's already a 1, so you can skip that step. So the next thing to do is to turn this spot into a 0. You're going to use the top row and add with the bottom row to help you do that. That gives you this new bottom row. The next thing to do would be to turn this into a 0. So you're going to use the middle row multiplied by 2 to help add with this. And that gives you this, 0, 0, 1, -5, 2, 1. You're right now in row echelon form, but we still have to get rid of these 3 spots that are above the diagonal. And you do them in this order. You're going to get rid of the 3 first, because you're working from bottom up. Then you're going to get rid of this 2, and that 2 is going to be last. So remember, you're working from bottom up and from right to left. So you'll have to do the bottom row multiplied by -3, add it with the middle row to get this new middle row. Then you'll take the bottom row multiplied by -2 and add it with the top row to help you get rid of this spot right here. That's going to give you 1, 2, 0, 11, -4, -2. And then you're going to use the middle row multiplied by -2 so you can add with the top row and get rid of that 2 right there. Here's your final answer. It took me 7 steps to get here, but here's what you get. And remember, it is only these things on the right-hand side of the dotted line that represents your inverse. It's not both of these. It's not the whole thing. It's just what's on the right-hand side. So -13, 6, 4, 12, -5, -3, -5, 2, 1. That's your inverse matrix for A. The last problem for this, something weird kind of happens. My top row is in really good shape. 1, 0, 0 looks great to me for the top row. In my second row, when I go to get rid of this 3 right here, that means you're going to multiply the top row by -3 and add with the middle row. You get all zeros on the left-hand side of that dotted line. Whenever that happens, that means this is no longer going to produce an inverse. This is what we call a singularity. So anytime an entire row in your Gauss-Jordan process turns out to be all zeros, you have a singularity, which is a square matrix that does not have an inverse. That's it for the solutions of these homework problems.